Okay, so we've already talked about the weak intermolecular forces. Now we're going to talk about the strong ones. And the strong intermolecular forces are covalent network, metallic, and ionic. And when I say strong, these guys are on a whole level of so much stronger than anything else that we've talked about. They tend to be solids at room temperatures. They're beyond anything hydrogen bonding or anything. So covalent network is found in elemental carbon, so primarily graphite, diamond, and fullerenes, which is a category, and anything containing silicon oxide, so like sand or quartz. So this is primarily it. There are essentially 4 of them, okay? That's it. That's pretty much the extent of them that are covalent network. They form a large network of covalently bonded molecules or atoms. So diamond and graphite are elements of carbon. They're different allotropes of carbon. So an amorphous version of it is coal. We're not really going to talk about that. Diamond is the hardest natural substance on Earth, but it's an insulator. Graphite, on the other hand, is very slippery, but it conducts electricity. Okay, or it's used as a lubricant on bikes, ball bearings on bikes. So different properties are explained by the way in which they form these covalent network bonds, but they all have relatively high melting and boiling points. So this is what diamond looks like. Carbon, 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 carbon. Carbon loves those 4 bonds, and it forms 4 bonds in this complex tetrahedral, sp3 hybridized, and it just keeps going out. It's this big network of atoms. Okay, they're locked into a tetrahedral shape. It is very, very strong. This is a sigma bond. Those electrons are being shared equally. And they're referred to as covalent network bonds. Okay, graphite has the same kind of situation. It's got those covalent network bonds between the carbon atoms, but it has these leftover p orbitals that are part of a pi bond that delocalizes and spreads over the entire molecule. So in graphite, we don't have the sp3 hybrids, we have sp2. And it is very strong within that hexagon at 120 degrees. However, because it's flat, what we have is we have these leftover pi bonds between the p orbitals, and those pi bonds are not held very tight. They're actually kind of weak. And so the pi bonds are above and below the plane. And so what you get is you get like these layers of pi bond and then graphite, carbon, 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 and then a layer of pi bond. So with these delocalized orbitals, the electrons are free to move. When they're inside here in that bond, they are not free to move. They're localized. They're not delocalized. And that's why graphite is very good about being a conductor, as well as because these are relatively easy to break, these layers, what you get is it breaks off a layer of graphite every time. So if you write with a pencil, pencils are layers of graphite, and every time you press down with that pencil, you're leaving behind little layers of graphite. It's kind of cool. So within those hexagons, very strong. Outside the hexagons, it's very weak. So that's covalent network. Literally 4 things. Metallic bonding happens in any elemental metal. So there's 88 of them or something like that. It is a very strong bond between the atoms of the metals. It creates this thing called an electron C model. And what that means is you have these metal atoms. Let's say it was iron. So you've got these iron atoms, and the electrons delocalize. They move away, they separate out. And it's basically a whole bunch of positive ions surrounded by a whole bunch of electrons. And that's why metals can conduct electricity very well, is because these electrons can move. And that's what electricity is. It's moving electrons, moving charge, essentially. Okay. They also can conduct heat. Metals are malleable and ductile, meaning you can stretch them out. These things slide past each other pretty well because they're not being held by those covalent bonds. They're being held by essentially delocalized electrons holding them together. Okay. Tends to have very high melting and boiling points. Ionic bonding is extremely strong attractive forces between the cations and anions to form what's called a large crystal lattice structure. Okay? They also have very high melting and boiling points. And the atoms are locked in the lattice, so they're hard and they're brittle. They're not like metals. They're not bendable. They're not malleable. They're not ductile. Okay? And they won't conduct electricity because those ions, the positive charge, and that's what electricity is moving charge, they're stuck. But when you dissolve them in the water, make them aqueous, or you melt them, all of a sudden those ions are free to move, and they will conduct electricity. Okay? What a crystal lattice looks like, this is sodium chloride. So you have Cl minus and sodium. Positive, negative, positive, negative, positive, negative, positive, negative, positive, like that. It just alternates it and it builds this great big crystal structure. If you want to see more about it in your book, you can certainly read about it in your book. The smaller the radius, the greater the attractive forces. That's Coulomb's law, because they can get very close to each other. And the greater the positive charge and negative charge, the stronger they get together. So these are your forces. Okay? It's on the back of your calendar. The first three are the weakest, and they go in order of the way they're written in terms of the strongest of those three and the weakest of those three. These guys right here are all considered the strong intermolecular forces. There is no ranking that I know of where this one's the weakest of the strong and that's the strongest of the strong. They don't do that. They are all just strong. These guys are all weak. But within those three, this one's the strongest and that one's the weakest. Okay? This breaks down how everything happens. A polar molecule is either dipole-dipole or hydrogen bonding or both. Well, if it's hydrogen bonding, it's dipole-dipole. And again, they get very stronger as you go. But when you get to this point, it's just very strong, very strong, very strong. Okay? So predicting the forces, this is positive and negative ion. This is ionic. Carbon, this is diamond, that's covalent network. This is an elemental metal, it's metallic. This is not covalent network. It is not metallic. It is not ionic. It's not one of the strong ones. It's actually this structure. Which means it's perfectly symmetrical. It's non-polar. That means it's LDF. Okay? And everything has LDF. I didn't write LDF for everything. The C2H5OH has the same structure except it's got an OH here. And because that H is polar covalently bonded to the O, this guy has hydrogen bonding along with dipole-dipole and LDF. Because it's asymmetrical, it's got dipole-dipole. NH3 looks like this. It's got dipole-dipole, LDF, and hydrogen bonding because the hydrogen is polar covalently bonded to the N. PCl3 is a very similar structure. So it's polar, so it has dipole-dipole and LDF, but it doesn't have hydrogen bonding, doesn't even have hydrogen. Argon is a noble gas, all it has is LDF.